Rule-based fraud detection in banking. Banks face the constant threat of fraudulent transactions that cost billions every year. Rule-based systems are widely used for detecting suspicious patterns in banking transactions. In this lesson, we will use Python to build, test, and understand rule-based fraud detection. You will understand transaction and customer data models. Learn to design and implement simple and complex fraud detection rules. Handle errors and edge cases. Build a mini end-to-end fraud detection engine. Running the cell now. We import pandas to work with tables and data frames. We import NumPy to handle numeric operations and randomness. We import warnings so we can filter out warning messages. We turn off all warnings so our notebook output stays clean. Running the cell now. Understanding the data we use for fraud detection. Our main data is a list of banking transactions. Each transaction has unique identifiers, amounts, types, channels, and timestamps. Customers have segments, retail or business, and regions, metro or regional. Common mistakes. Forgetting to match customer IDs across tables. Using unrealistic transaction amounts for rules. Ignoring the channel or time when designing rules. Running the cell now. Let us make a simple table of banking transactions to practice on. We set a random seed so the results are always the same. We choose 1,000 transactions for our synthetic data set. We set 200 as the number of unique customers. We create a table where each row is a transaction. Each transaction gets a unique ID. Transaction rows are linked to a random customer. We make up realistic transaction amounts, mostly around 150. We randomly assign debit or credit labels. We randomly pick the transaction channel. We set the transaction times as hourly across January 2024. This ends our synthetic transaction setup. We print the number of rows and columns. We preview the first 3 transactions. Running the cell now. This output shows our synthetic data set of 1,000 banking transactions with 6 key columns, including unique transaction and customer IDs, amounts, types, channels, and timestamps. Notice the varied channels and transaction types, which reflect the diversity of real data we'll analyze for fraud patterns. The shape and preview confirm that our data structure matches the intended format for building fraud detection models. Try changing n_transactions to 500 or 2000 to see what happens. How does this impact the preview? Now we build a table of customers including their segment and region. We list our customer IDs. We build a table with 1 row for each customer. Each customer row is assigned its ID. The first 150 are retail customers, last 50 are business customers. First 100 are from metro regions, last 100 are from regional areas. This gives us variety in our customer data. We print the number of customers and columns. We preview the first 3 customers. Running the cell now. This output shows our synthetic customers table with 200 rows and 3 columns, customer_ID, segment, and region. Notice the clear segmentation, most customers are retail, and the regions are evenly split between metro and regional. This setup helps us model different customer profiles accurately when analyzing transaction data for fraud detection. How many business customers are in metro regions? Try slicing the data frame to check. Let us begin with a very basic fraud rule, flagging high-value transactions. We set a suspicious amount threshold at 500. We flag transactions that are greater than 500. Add the flag as a new column. Show the first 5 transactions with their flag. Print how many transactions got flagged. Running the cell now. This output shows the first 5 transactions and a new column flagging amounts over $500, with none flagged here. Notice that all sample amounts are below the threshold, so the simple rule currently catches no suspicious transactions. This highlights how initial thresholding might miss many cases and the importance of exploring transaction amounts before setting detection rules. Try lowering the threshold to 200 for more flags. What do you observe? A second rule, flagging transactions done during times when fraud is more likely. We extract the hour of each transaction. We flag transactions that occur from midnight to 4 a.m. This creates a true-false column for odd hours. Show the flags for the first 5 transactions. Print how many total odd-hour transactions exist. Running the cell now. This output shows the first 5 transactions all occurring during odd hours, specifically between midnight and 4 a.m., as indicated by the flag_odd_hour column being true. Noticing that 210 transactions fall into this category highlights that a notable portion of activity happens during these unusual times, which could be relevant for detecting potentially fraudulent behavior in our dataset. This step sets the foundation for exploring time-based patterns in fraud detection. Do you see any overlap between high amount and odd hour flags? A third simple rule, online transactions are often riskier, so let us flag them. We flag any transaction whose channel is online. Show the first 5 transactions with online flags. Count how many transactions went online. Running the cell now. This output shows the first 5 transactions with a new column, flag_online, indicating whether each transaction was made via the online channel. Notice how only the rows where channel is online have true in flag_online, confirming the filtering logic works correctly. The total count of 236 online transactions helps us gauge the prevalence of online activity in this dataset, which is key for targeted fraud detection strategies. Most fraud monitoring systems have stricter rules for online transactions. Why do you think that is? Let us combine 2 rules, high value and odd hour. These are more suspicious cases. We use logical and to flag transactions that meet both conditions. Show relevant columns for 5 transactions. Print the number flagged for both high value and odd hour. Running the cell now. This output shows the first 5 transactions and a new flag combining high amount and odd hour conditions. Notice that none of these early transactions meet both criteria simultaneously, as reflected by the 0 total flags. This confirms our logical check is working correctly to identify potentially suspicious transactions for further fraud analysis. Try changing the time window or amount and observe how the joint flag count changes. Let us create a rule for retail customers specifically, only flag big amounts for them. We get the customer segment from the customers table. Attach segment as a new column in transactions. Flag if segment is retail and amount is greater than 800. Show first 5 relevant transactions. See how many retail transactions are flagged. Running the cell now. This output shows the first 5 transactions with added customer segments and a flag for high-value retail transactions over 800. Notice that none of these sample transactions meet the threshold, resulting in 0 flagged cases so far. This confirms the code correctly applies the flag only to retail customers with very high amounts, helping us focus fraud detection efforts on significant retail transactions. Why might you want different rules for business and retail segments? Abnormal rapid activity can be suspicious. Detect if a customer has several online transactions in the same hour. Count the number of online transactions for each customer within each hour. Flag this situation if there are 3 or more for the same customer an hour. Show a few flagged online burst cases. Print the count of such events. Running the cell now. This output shows no instances where a customer made 3 or more online transactions within the same hour, as indicated by the empty data frame and 0 flags. This highlights the importance of verifying that our burst detection logic captures actual patterns in the data. Here, the chosen time grouping or flags may need adjustment to detect suspicious online activity effectively. Understanding these counts ensures we accurately flag potential fraud without false negatives. What about bursts on other channels? Try extending the rule. Now let us add a rule for channels and regions. Maybe big ATM withdrawals in regional areas are more suspicious. Get region information for each transaction. Map the region onto each transaction. Flag if a channel is ATM, the region is regional, and amount is greater than 600. Show up to 5 such flagged cases. Print the total flagged for this rule. Running the cell now. This output shows no flagged transactions where an ATM withdrawal in a regional area exceeded the $600 threshold. This confirms that, in this sample, such anomalies are either rare or non-existent, highlighting the importance of setting and validating precise detection rules. Noticing an empty result helps us understand data distribution and avoid false positives when monitoring for fraud. Channels and regions together can lead to very specific, actionable rules. Most systems do not use a single rule, but a combination for a fraud score. Let us build one. We create a fraud score by assigning different point values to each flag. High amount gets 2 points. Odd hour adds 1. Online adds 1. High amount and odd hour together is even more risky, so +2. Online bursts are very risky, so +3. ATM regional anomaly adds +2. Show some results. See the distribution of possible fraud scores in our data. Running the cell now. This output shows the first few transactions with their combined weighted fraud scores, highlighting how different flags contribute to the total. Notice most transactions have a score of 0 or 1, indicating low or no suspicious activity, while higher scores like 2 are less common but signal increased fraud risk. This reinforces the lesson's intent. By combining multiple indicators with weights, we create a more nuanced fraud detection score that better prioritizes risky transactions. Try tuning the weights. What changes most in the score distribution? Finally, let us show how you can use the fraud score to only flag the highest risk transactions. Flag transactions if their score is more than 5. Show transaction IDs and their scores for the highest risk cases. Print how many were classified as potential frauds. Running the cell now. This output shows that no transactions currently have a fraud score above 5, meaning none are flagged as potential fraud. This highlights the need to review our fraud scoring threshold or data distribution before relying on this filter for detection. It reinforces the lesson's focus on carefully understanding and validating how risk scores relate to real transaction patterns. If you lower the score threshold, do you think more or fewer transactions get flagged? Let us see what happens when data is missing, a very common beginner error. Create a copy of our transactions. Intentionally set some amounts to missing NaN. Try running our flag rule on these values. We use try except to catch errors. If there is an error, print it. Show the affected rows after running code. Running the cell now. This output shows the result of applying a comparison to the amount column, which now includes missing values, NaNs. Notice that the new flag_missing_error column safely handles NaNs without raising errors, marking all these rows as false instead of breaking the code. This demonstrates the importance of error handling when working with incomplete transaction data in fraud detection. Do you see why missing values can break rule logic? How would you fix this? A common solution is to fill missing values before applying rules. Fill missing amounts with 0. Flag according to the filled value. Show the outcome on some rows. Running the cell now. Here, we handle missing transaction amounts by filling them with zeros to avoid errors during flagging. Notice how the amount_filled column replaces nans with 0, and the flag_filled column shows false since none of the filled or original amounts exceed 500. This ensures consistent flagging without dropping or misclassifying transactions due to missing values. What are risks of filling missing values with 0 in anti-fraud use? Sometimes, reporting missing critical information is as important as reporting fraud directly. Check if amount, channel, or customer_ID are missing for any row. Add a flag if there is missing info. Show the flags for the first 10 transactions. Print count of missing info cases. Running the cell now. This output shows the first 10 transactions with key columns checked for missing values, amount, channel, and customer ID, and a new column flagging any missing info. Notice that all rows are complete with no missing data, as confirmed by the 0 count at the end. This verifies the dataset's integrity, ensuring critical information is present before building fraud detection models. What are some other columns that should never be missing in fraud detection? A good habit: wrap your rule logic in a function for clarity and reuse. Define a function for the large transaction flag. Return false if amount is missing. Return true only if amount is above the threshold. Apply function to each transaction's amount column. Preview its results for a few transactions. Running the cell now. This output shows the first 7 transactions with their amounts and a new column, flag_func_large, which marks transactions above $500 as true. Notice that all flagged values are false here because none exceed the threshold, confirming our function correctly identifies only large transactions. This demonstrates how encapsulating fraud logic in a function ensures clear, reusable flagging during data exploration. Try adjusting the function threshold or logic. Can you make it handle another flag as well? It is helpful to summarize all flagged rules in a single column for reporting. List all the flag columns. Create a summary flag if any rule is triggered. Show some transaction IDs and their summary flag. See how many transactions triggered at least one rule. Running the cell now. This output shows a new column **flag_summary***, which combines several individual fraud detection rules to indicate if any rule flagged a transaction. Notice that out of 1,000 transactions, not shown fully here, 394 are flagged as suspicious, while 606 are not, providing a quick overview of potentially risky transactions. This helps us efficiently summarize multiple risk signals and focus our attention on transactions most likely involved in fraud. How would you summarize which rules triggered? Try building a text summary instead of just true/false. Let us bring everything together. Create a report of all flagged transactions. Filter all transactions that have been flagged. Select the relevant columns for reporting. Prepare a summary data frame. Export the flagged results to a CSV file for follow-up. Show a preview of the report. Print total number of cases reported. Running the cell now. This output shows a sample of transactions flagged by our fraud screening, including key details like transaction channel, customer segment, and fraud score. Notice that flagged transactions come from both retail and business customers across metro and regional areas, with fraud scores indicating suspicious activity. This confirms our code successfully filters and exports the relevant cases for further investigation. Opening the generated CSV file of flagged transactions for review. Now you have a real workflow for analysts to investigate suspicious transactions. Share this lesson or revisit the notebook again. For more banking data science, search YouTube for Python Fraud Detection Banking.